Okay, so we completed chapter 1. We'll proceed ahead with chapter 2, which is theory of vibrations, and we'll see how far we can go the next 20-30 minutes. Just the introduction part, then we'll stop it for next week. So content-wise, we're trying to cover in this chapter, we'll define definitions and terminologies for vibration. We will see the spring mass damper model, and especially we'll see examples of a foundation, because this class is specifically for geotechnical engineers, soil dynamics course. Most of our examples will be a spring mass damper model for our foundation example, but the theory of vibration, it has a wide application, even outside civil engineering. There is a structural application, structural dynamics. There is also a mechanical engineering application for, cars, motors, and many equipments. But this course is specifically geared to like a soil dynamics foundation related. So most of our examples would be in that area. But keep in mind, the concepts are applicable anywhere. And we'll see general equations of motion for externally applied force, general equation of motion for ground seismic motion. These are general equations of dynamics. They can be anywhere, but we'll specifically be discussing application on civil engineering and especially geotechnical engineering. And the single degree of freedom systems will have a wide coverage on it, because to see a more detail on a complex model, like more than 1 degree of freedom system, we need to understand it. So most of the coverage will be for 1 degree of freedom system. And in terms of free vibration of the spring mass system, forced vibration. Forced means we are applying force, constant force on it. Free is just you apply initial force, then you let go. It moves by itself. And we'll see free vibration of the SMD system, forced vibration, SMD system. Now we have damping introduced in it. The first two were without damping. The second two are, there is SMD as a damping applied. The first two were only spring and mass. Now we introduce damping. And we'll see how forces transmit due to a vibration to other structures. And rotating mass type excitation, damping ratio, concept of damping, and a MSD model for various models of vibration of foundations. And the last part would be a multi-degree of freedom systems. That's usually 2 degree of freedoms and beyond. The concept is the same way. It's like extension of 1 degree of freedom system to others, more complex, but it becomes also more complex for a hand calculation, for empirical equations. So for multi-degree of freedom system, we use computers mostly to solve it, but most of the understanding comes from a single degree of freedom system. So the first section, which is definition and vibration terminology, we're trying to cover, seismic vibrations, but when we say vibration, it's a wide topic. It's any oscillation, any back and forth motion. For example, it can be like a pendulum swinging back and forth. That's also a vibration. You have a pendulum, moving up, and give me a second. So I'm sharing the slides, which is better than the PDF for your review. For me, it doesn't matter. So with the pendulum example, you have a pendulum swinging up, and then at the highest point, it's almost velocity 0 point, all potential energy then swings back. So this back and forth motion, or a machine foundation vibration. There can be a motor vibrating on a machine foundation, applying a vertically sinusoidal kind of motion, a pendulum continuous motion, and that motion goes to the foundation, and from the foundation, it goes to the soil. We'll see detail on this. Or It can be also a vibration caused by earthquake. You can have ground shaking and buildings responding to it, like a seismic input, like this. Or it can be like a vibration caused by wind. There can be numerous examples of vibration, but generally any oscillations, back and forth motion, whether it's regular or irregular, that's what we call vibration. And there are some terms to know for vibration, like a periodic motion is a motion which repeats itself in a regular interval of time. If you see the plots at the bottom on the left side, this is what we mean by if it's regularly repeating itself, this is one cycle up to here, then another cycle starts right here and it goes, and it repeats infinitely or for some time. Those regular pattern motions, we call them periodic motion. And this can happen even what it looks like irregular here, the displacement time plot, if you see it at the bottom, but it's regularly repeating itself. This first portion, the second portion, if you see it, it's repeating itself, even if it looks like irregular, per individual times, specific around this area. So these kind of motion which repeats itself with certain specific time, we call them periodic motion. Or if it is like, simple to call it the first one, simple harmonic motion, which is like, you can represent it with the sine and cosine functions. That's what we call them, simple harmonic motion. But this one, you may not capture with simple sine and cosine functions. And harmonic motion is a periodic motion where displacement varies sinusoidally with time. The motion can be represented by sine and cosine function. That's the first one we talked. But still you can have periodic motion, even if it's not harmonic motion. Non-periodic is, motions, vibrations, which doesn't repeat itself. For example, like this. This can be like explosion. When you model like a bomb explosion or a nuclear explosion or anything, all of a sudden it peaks and it disappears within 1 or 2 seconds like that. It dumps out. Or it can be a seismic motion. It starts right here, vibrates, then at some point it dies out. The energy dissipates. And also it doesn't repeat itself. If you see the peaks at different time, they are different. So it's not repeating itself time after time. So this is irregular. So we call it non-periodic, or it's called also aperiodic. So non-periodic can be transient motion, respond to impact loading, like explosion or like that. Or it can be transient motion, earthquake ground motions. Now, simple harmonic motion parameters, we have been talking a little bit on period. When I mentioned about the seismic, the 1985 earthquake damage on Mexico City, we talked about period. We talked about how that the period of the building matches with the period of the soil and resonance occurring. This is where we define the period. Period is the time it takes for one complete cycle. Let's say you have a spring, a suspended spring, and without the mass, the spring alone, maybe this is its position. If you add some mass on it, there is a static displacement extending up to here. So this is let's say with the mass, the neutral position. Now give it a little input initially and let go. What happens is it oscillates back and forth about the neutral point, the static neutral point. So this is now vibrating. In the static case, it wasn't vibrating. Now this is vibrating. Let's try to define how it vibrates with plots. So let's say it's moving up and down. At any time, you can track it and see how its displacement varies with time. This one complete cycle, which means it moved, let's say initially you gave it an input upward, then you let it go. And it starts from here and move down, cross past the neutral point, it comes back and move up. This one complete cycle is what we call, this chart is showing. So this is amplitude is the maximum, the distance. This is less distance, or in this case, height. The Y is showing you the height of the motion of this ball or this mass. versus time. So if you plot it, you will see a chart like this. So this period is the time it took for one complete cycle. It starts from a 0 point, goes up, comes down, and comes back to the 0 point. So this one complete cycle, if you plot it, that's what the displacement time looks like. And that time, the period for one complete cycle, that's what we call period. And it has a unit of time, because basically it's a time for one cycle. So amplitude, when we say amplitude, is the maximum motion of this mass, either upward or downward. So when you say amplitude, it's either direction. It's the absolute value of the maximum displacement. It can be down, you may call it negative, but the absolute value is the amplitude, whichever is large. For a periodic motion, it's uniform, one after the other. So amplitude is the maximum displacement, but you have other displacements at different times. The peak one is the amplitude. Period is the time it took for 1 second. So you can simulate the same motion like for this spring. We can also model it with a sine and cosine function. This is basically a sine and cosine function. You can represent it. It's a sinusoidal motion. That's what we said, harmonic motions. Any motion that you can represent with sinusoidal functions, sine or cosine, that's a harmonic motion. This is spring motion. It's an example. Now, there is a catch behind it. There is assumption behind it. Here, we're not assuming damping. There is air resistance. Once you initiate this spring to move, it's not going to be infinitely like this. After some time, it starts dissipating, and then the motion becomes zero. It comes to a 0 point because the energy dissipates, because of air resistance, because of heat and everything happening in the spring itself, and so many things. But if you ignore all those assumptions, air resistance, everything, you have this periodic motion. This periodic motion, you can represent it. It's like going around a circle. Basically, if you see all this, it's like up and down motion or a pendulum motion. It's basically going around a circle. If you track it with a theta motion, the object can start from 0, go around, pass the 0 point, and make one complete cycle. So this can be described with this, with simple harmonic motion representation. With this, it's theta is the displacement now, and this height is the y is the displacement. So you can have displacement versus theta and the same plot at any time t, from the moment it starts motion to anywhere it is located. When it is located here, this is the location. So you know exactly. So this is a periodic motion or harmonic motion representation. So theta, you know that's omega t, omega is 2 pi f, which is the angular frequency. And now, once we define the period, the inverse of a period is what we call frequency. It's another term in simple harmonic motion. Frequency is the number of cycles per unit time, reciprocal of time, or it tells us how often a cycle repeats. If you have a specific time, let's say if you are measuring this, and within this specific time, how many cycles we have, that's what frequency is telling us. In simple harmonic motion, the sine cosine functions, you can have, I'm sure you know this from your math, you can have a displacement theta graph, displacement time plot, where xt is a displacement at time t. You can have a shift, or am is amplitude. The maximum peak value is the amplitude, whether it is in the negative or positive direction. Omega t plus phi is phase. You can have a phase of 0 when you start, or you can have a plus angle or a minus angle. Depending on where you start, you can have all this different character of a sine cosine function. Usually we use sine, but cosine function is also another representation. Omega is angular frequency, angular displacement per unit time. Phi is phase angle or phase constant. It defines position of the mass at time t is equal to 0. It can be 0 if it's at t is equal to 0. And frequency, we mentioned, we already defined it saying it's a reciprocal of time or how many cycles we have. For example, if you have different vibration with different period, for this, for the top one, the period is, or the time it took for one cycle, it goes up here, down here. This is what the period is. And if you see it, the one at the bottom, it starts here, and up to here is one cycle. After that, it's repeating itself. So this one has a shorter period. This one has a longer period. A longer period, we call it low frequency. The frequency, because frequency is the inverse of period, you have very few cycles within a certain period of time. But this one is a lot of cycles happening. When it's a lot of cycles, we call it high frequency. When very few cycles, low frequency. These are very big concepts when we go deeper into the course, because depending on your building frequency, now taller buildings are acting like this with a longer period, low frequency. But shorter buildings, they are high frequency with a lower period. So depending on the period or the frequency of your building, that's how seismic motion selectively attack. Or the concept we call resonance for the good example of the Mexico earthquake. Then that's what resonance, that's what selectively buildings from a story of 5 to 15 stories, they get damaged because it was closely matching the period of the soil and the amplified motion. So this has a big concept, just be aware of it. And the other term is damping. Damping is just the dissipation of energy. We have oscillations, but because of damping, it can be air resistance, it can be friction, it can be heat generating. Because of several factors, the peaks are not repeating themselves with equal height. So the energy is being somehow dissipated and finally stopping. So that's called damping. Degree of freedom. Degree of freedom, it's the number of independent coordinates, example, displacement coordinate system, required to describe the solution of a vibrating system. If you have a spring mass system, if it's vibrating, the location of this mass at any time t can be described with one coordinate system, z. So we call it 1 degree of freedom system. If you have two masses with two springs and vibrating, one coordinate system will not be enough. For example, this coordinate system tells us the location of this mass, but it cannot tell about the location of the second mass. So we need a second coordinate system. This is assuming only vertical vibration. So you need two coordinates, so we call it 2 degree of freedom system. Or you can have a spring mass system like this, but also doing rocking kind of motion. Now for the vertical motion, because it's a single mass with two springs, a single vertical axis could have been sufficient. But now there is a rotation component attached to it. So it's also rotating. So a vertical axis z plus a rotation theta. So we need 2 degree of freedom system. That's what degree of freedom is. And for example, if you see a pendulum swinging, how many coordinates we need to describe its motion? Just angle is enough, theta is enough. If we define the theta, we can say we know exactly where that mass is. We know exactly, if we know theta, we know exactly how high it is from the neutral position. So only one coordinate is enough. So a pendulum swinging is with a rigid string here, is 1 degree of freedom system. How about if you have a pendulum, but with a spring? Now look how it acts. It's also moving up and down with the spring. The spring is extending and contracting. At the same time, the mass is rotating. It has a rotational motion. It has also axial motion, in the axial direction of the spring. So you need two coordinates. For example, this theta will tell you exactly what location it is. However, the spring is contracting when the mass is at the top. It's shorter. So you need another coordinate r. So you need r and you need theta. So these two are sufficient to define the motion of this spring mass pendulum system. So it's a 2 degree of freedom system. Now, even if we start at 1 degree of freedom and 2 degree of freedom system, honestly speaking, a rigid body has a total of 6 degree of freedom system. It can translate in 3 directions. Let's say this x direction, in the longitudinal direction, or in the perpendicular direction. It can move, slide sideways, or it can move up and down also in the vertical direction. Those are 3 translations. Or it can rotate about those axes. We call it rocking when it is rotating about the longer axis, this rocking, or rocking about the shorter axis, which is the pitching, or yawing or torsion is rotation about the vertical axis, this way. So in general, to define the motion of an object, you need 6 degree of freedom system, especially for rigid body. Translation, 3 translation, and 3 rotations. But trying to analyze 6 degree of freedom system in one single equation, that's too complex. So what we will do in this course is we will start from 1 degree of freedom system motion. Just it can be horizontal, it can be vertical, or it can be rotating. We'll pick one of them and understand the concepts, then develop the concept to a higher mode of vibration, 2, 3, 6 degree of freedom motion. So that's the idea here. It's complex to analyze it as a single shot as a 6 degree of freedom, especially with equations, analytical equations. But that's what finite element softwares, they do it in one shot. But we'll see that at the end. But our strategy would be first consider only one direction motion, understand the concepts, then go to a higher level of modeling with a higher degree of freedom system. And spring mass damper models. Let's go the next maybe 5-10 minutes and we'll stop the class. The spring mass damper model, especially for geotechnical engineering application, let's assume you have a machine foundation block concrete, let's say rectangular block concrete. Then a machine is sitting on it and applying force on it because that machine is working. It can be applying anything. For now, let's consider only a vertical vibration of that machine. So the force from the machine, it goes to the concrete block foundation, then it goes to the soil. We can model this in a simplified way by assuming the mass of the concrete block plus the mass of the machine. So we can call it as a rigid mass. And we can represent the soil with a spring, it's elastic compression, contraction, property with elastic spring, or that spring constant, K. And also the damping character of the soil with a dashpot. So this is what the mass, the spring mass damper model is. So we're trying to simplify the complex character of a soil by simple representation of with a spring, mass, and damper. So mass is mass of foundation and load supported by a foundation. K is elastic stiffness of soil, can be obtained from soil load test like a plate load test. You can find, if you do several plate load tests, you can find the load you are applying and the corresponding displacement. So for that, you can determine the spring constant. Or C, damping representation dissipation of energy. It can be by friction of soil particles, or a heat, or a reversible deformation of particle, crack, and sound. So there is some dissipation of energy when you apply some load to soil. That dissipation of energy is what's represented in the dashpot. And Q is externally cyclic force on the foundation. That's what the foundation applied. Let's say a sinusoidal motion, so it's constantly being applied. SMD model with single mass is called single degree of freedom system. But the concept can be extended to multiple degree of freedom systems, can be 2 and above. Let's say practical example of single degree of freedom systems. For example, if you have a one-story building, you have the roof, and you have the stiffness of the columns and the beams there, which is a stiffness system. So you can really, if you see the vibration of this one-story building system, it's horizontally moving back and forth. So with a rigid mass. So the mass of the columns, the beams, and the floor, you can assume it's rigid. And the stiffness resisting that motion from the columns, we can calculate this in K. So in reality, as a simple model representation, a single story building can be represented by a single mass and a single spring. Or other example is offshore platform. You have, offshore platforms. Yeah, sorry. Let's say you have this offshore structure. It's a steel structure, steel frame structure with a foundation at the bottom of the lake or ocean, wherever it is. And you have a wave, a water wave acting on it. So the source of vibration of this structure, it's a water wave, water hitting it. Now, so there is back and forth vibration, and there is a significant large mass at the top supported. So the mass of the frame and this, you can represent it as mass, and the stiffness of this framing system as K. So rigid structure, well, this is together. We call it a flexible foundation, which means the framing system. We are assuming this rock is rigid. So that's the rigid part is this one. And the source of the motion is wave excitation. So tidal waves causing the motion. A car model as 1 degree of freedom system. Usually in civil engineering, we don't deal with cars and how they move, but mechanical engineers, that's how they apply this concept as for. For example, a car moving on an irregular road. Now, if it's irregular, you have that up and down motion. In addition to the constant motion of the car horizontally, you have up and down vibration. So that vibration is caused by irregularities on the road. So road irregularities is a source of motion. And let's say this is flexible suspension. You have the strut here. Flexible suspensions are assumed the K. This is assuming the tires are rigid. And the tires are receiving the irregular motion of the road. Then the mass of the car. So a single degree of freedom system can simplify the model of a complex motion of a car. The vertical motion, don't be confused here. The car is also moving horizontally, but it's not vibrating horizontally. It's a constant motion horizontally. But vertically, because of a road irregularity, it's moving up and down. So you can represent it like that. Or a motor generator as 1 degree of freedom system. If you have a motor generator on a foundation, you can represent this. Usually, we use dampers at the bottom of the motor, which is flexible mounts. So to reduce the force on the foundation, let's say this is a foundation. In this case, we're assuming it rigid. But that flexible mount, the pads we are using, it's acting like a spring. The flexible mount is now the spring. And the rigid mass of the motor is now, it's a mass, 1 degree of freedom system. And the motor, this periodic motion, it's from the motion of the motor itself. Or if you do 1 degree of freedom is a simplified model of structures, because the real systems have more than just 1 degree of freedom system. It's a simplified version. It gives you a reasonable answer and a quick one. But in reality, almost all objects, components, they are multi-degree of freedom system. For example, you can see a building. We have a building. In the worst case, you can simplify it as 1 degree of freedom system, but your solution would be very approximate. You're far, far away from the real solution. It can give you a good hint, but to find a reasonable answer, you have to consider multi-degree of freedom system. Let's say wherever you have significant mass, for example, the floor, the slab right here, it's a significant mass. and also the weight of the beams and the columns or walls. You can lump it. If you lump this mass, you have one mass. But the upper floor is also flexible. It has some stiffness. So we can consider that stiffness in K2. And the third floor is also, it's flexible. This column, K3. And we can have 3 masses and 3 springs. And wherever the springs are also, there is damping occurring, so damping. So you can have a multi-degree of freedom system. In reality, when you model a complex building in finite element model, for example, in SAP or in STAT, it's thousands of freedom system you are modeling. But we're approaching it from a single degree of freedom system, then a 2 degree of freedom system, then you'll understand how everything is getting complex. Let's say 2 degree of freedom system, forging unit with impact load as 2 degree of freedom system. You have a foundation block for a forging unit. That forging unit, the way it works is there is a mass dropping, and that's cause impact. So that's how the forging happens. And there is a block, the anvil block, that's receiving the impact. You may have a metal that you're forging. So if you see this mass dropping on the anvil is another heavy weight. There is elastic pad. We are trying to protect the foundation. So that elastic pad is damping out the energy. So that elastic pad, it has a stiffness and damping. So damping of elastic pad, you see it here, the damping and the stiffness. The mass of the anvil and the mass of that dropping object right here at the top. Now, right below the elastic pad, what do you have? A mass of concrete block. You have a concrete block. So you have 2 masses at least in the model. Now, let's assume this is not rock. This is not rigid. Let's assume this is soil. If it is soil, then it has some elastic and damping character also. Then this is the soil, damping, and the stiffness part. Now the soil, let's assume it's resting on a rigid rock. The movement is almost negligible. That's the rigid rock you have. So you can model this as a 2 degree of freedom system. Or you can have a car with flexible tires. Now if you consider the tires are flexible, and the suspension with multi-degree of freedom system. On the car also, it's not only oscillating back vertically up and down, it can also, depending on the road irregularity, it can also rock, right? Can also do some rocking motion. So you can have a rocking motion, the mass of the car, and then the tires, flexible suspension. The suspension is right above the tires. That's where most of the energy is damped out. So the first K can be the suspension, then the mass of the wheels. The wheels are the tires. Then the tire is also, we assume it's flexible. Then the flexibility of the tire as K. In this case, we didn't account for damping, but you can add also damping. So you have these 3 degree of freedom systems. So depending on your model, it can get complex. It can get simplified to 1 degree of freedom system. Okay, I think it's good enough for this class until it's the end of section 1.2. Next week, Mondays, same time, we can continue from general equation of motion.